Hello everyone and welcome to the module 4 first lecture, gradually varied flow. In the previous modules we have discussed basics of open channel flow, uniform flow, and also the critical flow. So all these concepts are synthesizing here and delivered together in gradually varied flow. So the learning objectives of this lecture is to understand the assumptions involved in gradually varied flow analysis. Then we will derive the governing equation of gradually varied flow and its other forms. And finally, we'll analyze the characteristics of flow profiles. So as you know, gradually varied flow is a non-uniform flow. So whatever discussion we'll do henceforward will be pertaining to non-uniform flow. Uh, So that will be gradually varied flow. Then in coming modules, we'll have rapidly varied flow and so on. So in a gradually varied flow, so essentially it is a non-uniform flow. However, we are considering only steady non-uniform flow at the moment. The unsteady part we are not discussing now. So the non-uniform flow, as you know, it changes its depth or discharge or velocity at its move, or in general we can say it changes its depth as it moves along the channel. So dy by dx, that is not equal to 0. So that is the non-uniform flow. Now, what can be the reasons for change in depth? The very first reason can be change in the cross-sectional shape. So as we all discussed previously that the canal is a rectangle trapezoidal canal, and it has to cross a river or any other nala. So we have an aqueduct. So for that the cross section is made rectangular. So that may induce non-uniformity of the flow. If there is some change in the discharge along the channel, if the discharge is added or subtracted into channel, so that may also cause non-uniformity. If there is presence of any control structure, like if there is a dam or a weir, then also there can be non-uniformity. If there is a sluice gate that is controlling the flow, again there is a non-uniformity. And if there is some change in the bed slope, so originally the slope of the river is mild and there is some natural topographic gradient where it is steep, so usually the waterfalls where all of a sudden you get a very abrupt drop, so there is a change in the slope. So these all conditions may lead to non-uniformity in the flow. So thus, to summarize, that in case of a non-uniform flow, the depth, discharge and velocity varies with space. So dy by dx, dv by dx and dq by dx are not equal to 0. So again, the non-uniform flows are gradually varied, rapidly varied or spatially varied flows. Now moving on to the GVF theory. So we have certain assumptions as discussed earlier, that we will be considering the flow to be steady. So the hydraulic characteristics of the flow that remain constant with respect to time. So that is a very first assumption. Second, since in a gradually varied flow, the change in the flow profile is very gradual, so we'll consider that streamlines are practically parallel and the hydrostatic pressure distribution would prevail over the channel section. So there is no abrupt change in the streamlines, so they are practically assumed to be parallel. Now these two conditions signify the GVF flow, but there is a very basic assumption which is involved, and that is the head loss at a section is same as for a uniform flow having the velocity and radius of a section. Now gradually varied flow is agreeably a non-uniform flow, but we consider that the assumptions made or the considerations of the uniform flow, such as the loss equation, the resistance equation, that is a Manning's equation, is equally applicable in the gradually varied flow analysis. So you know the Manning's equation, V equal to 1 by n r raised to 2 by 3 s naught. Now, if you were to apply this uniform flow equation, that is the Manning's equation, to gradually varied flow, so the bed slope S naught is replaced by the energy slope. So the energy slope SF is computed as n square v square upon r raised to 4 by 3. So when we are applying Manning's equation to this GVF, your S naught becomes SF. So that brings us to a discussion question that in GVF, the energy loss is mainly due to which factor? It is due to the boundary friction, or is it due to large scale eddy currents? So mainly in case of flows where there are two components. One is a resistance due to the bed material that is causing the friction, and second, the vortices which are generated, that is the eddies. So usually the eddies would come into picture where there is unsteadiness of flow, where there is some rapidness involved. So that are the aspects which you need to think upon. Now there are some additional small assumptions. That is, the slope of channel is very small. Obviously, if the channel slope is very large, there may be chances that there can be some rapid changes in the flow. So the depth of flow is same whether it is measured vertically or normally to the bed slope. The pressure correction factor cos theta becomes 1 and there is no air entrainment. Second assumption is that the channel is prismatic, that is, it has a constant alignment and shape. Then the velocity distribution in the channel is also fixed. So the velocity distribution coefficient are constant. So alpha would be equal to 1. The conveyance K and the section factor Z are exponential functions of flow depth. So they vary exponentially with the flow depth, and the roughness coefficient is independent of depth of flow and constant throughout the channel under consideration. So that is also a very important assumption, that we saw that usually the roughness coefficient varies with the depth, but here we are assuming constant across a cross section. Now let us derive the dynamical or the differential or the governing equation of a gradually varied flow. So let us understand the schematic first. So in this we have a channel of bed slope theta, that is so the bed slope is having the angle theta. So this is the length, that is dx. The bed slope is denoted by S naught. Then it is above the datum. So z is the datum height. Then the depth of flow is denoted as y. So this water surface, you can see it is gradually changing over the length dx. So the water surface slope is denoted by SW. And then you have energy line, that is y plus v square by 2g, that is the specific energy, and the energy slope is denoted by SF. So dH is the fall in total energy or total head, that is summation of datum head plus depth, that is the flow depth, and the velocity head. So dH is the total, the loss of total head in the length dx. So we know that H equal to Z plus E, that is the datum head plus specific energy, where E is equal to Y plus V square by 2G. So we'll carry forward this equation. Now, since your water surface varies in the longitudinal direction, so your Y and E, that is the depth and specific energy, are function of X. So let us differentiate equation 2. So here it will be equation 2 with respect to X. So we get dH by dx is equal to dz by dx plus de by dx. So this becomes dy by dx plus d by dx of v square by 2g. So it has three components. So let us understand what these three components are. So the first component, that is dH by dx. So that is the energy slope. So that is change in energy, and it is denoted as minus SF. Why the negative sign? Since it is decreasing in the direction of flow. So that is why we are considering it as negative. Now dz by dx. So that is the bottom or bed slope, and that is denoted by minus S naught. And dy by dx, that is a water surface slope relative to bottom of channel. So it is related to bottom of channel. And now this component will resolve in detail. Now, so dy by dx is water surface slope related to bottom of channel, that is S naught. So if you want dy by dx with respect to horizontal, so that is a water surface slope with respect to horizontal, so it will be dy by dx minus S naught. So then you are discussing it with respect to the horizontal. So let us resolve this d by dx of v square by 2g. So v square by 2g, that is cube square by 2ga square, and since a is a function of y, so here dy by dx is additionally introduced. So on differentiating we get minus q square upon ga cube into dA by dy into dy by dx, but dA by dy is t, that is the top width of the channel. So this equation becomes minus q square t upon ga cube. So this is very similar to what you had for the critical flow, that is q square t upon ga cube is equal to 1. So let us rewrite the equation 4. So this dH by dx was minus SF, dz by dx was minus S naught, dy by dx as it is, and this d by dx of v square by 2g comes into picture. So let us take S naught to the LHS. So the S naught goes to the LHS. So S naught minus SF, dy by dx is common, 1 minus q square t upon ga cube, and dy by dx is equal to S naught minus SF upon 1 minus q square t upon ga cube, and this is the governing equation of gradually varied flow. So you are interested in finding what is the change in the depth of flow, and thus this equation helps you quantify the non-uniformity in the nature of gradually varied flow. So what are the dependent parameters? You need the energy slope, you need the bed slope, you need the discharge, you need the geometric properties. So these are so here it will be requiring the concepts of both uniform flow as well as the critical flow. So now we know that F is equal to V upon under root GD, and that is V upon G into A by T. So D is A by T. So that becomes, so this q square t upon ga cube is nothing but f square, and this equation can also be written in terms of Froude number, that is dy by dx is equal to S naught minus SF upon 1 minus f square. So this is again another form of the basic or governing dynamic equation of gradually varied flow. So this equation has some other forms. So we have the modified forms, and would one by one look at these modified forms of the equation. So first we discuss about the conveyance. So you know conveyance is a discharge carrying capacity per unit longitudinal slope. So conveyance at any depth y, that is k, and kn is conveyance corresponding to your normal depth yn. So the uniform flow equation, q is equal to kn under root s naught, where s naught is q square upon kn square. So based on the assumption of GVF, when we apply the uniform flow equation, as I discussed previously, S naught can be replaced by SF. So for the GVF case, Q is equal to K under root SF, where SF is equal to Q square upon K square. So we get this equation 10 and 11 in terms of the conveyance. Now, let us compare these equations, and we get SF by S naught is equal to Kn square upon K square. So this is equation 12. So we are just keeping it aside. Now we'll move on to the next part, then we'll use that later. Is the section factor Z. So the section factor Z is at any depth y, and ZC is a section factor at critical depth yc. So that is a section factor at critical depth yc. So the section factor is given by z is equal to under root a cube by t. So z square is equal to a cube by t, and zc square, that is a cube by t, that is for the critical condition, and that is q square by g. So because we have the relation q square by t upon g cube is equal to 1, so let us compare the equations 13 and 14, and you get zc square upon g square, that is equal to q square by g upon a cube by t, and you get gc square upon g square, that is equal to q square t upon ga cube. So this is equation 15. There we had equation 12. Now let us use both 15 and 12, and we substitute in equation 9. And so we have it was s naught minus sf, so we are taking s naught common or dividing by s naught the numerator, so it becomes 1 minus sf by s naught into s naught, and the denominator is 1 minus q square t upon ga cube. So this is in terms of conveyance that we are substituting here, and this is in terms of section factor. So the final equation is dy by dx is equal to 1 minus kn upon k the whole square upon 1 minus zc by z the whole square into s naught. So this is another form of your gradually varied flow equation. So now let us move on to discharge. So we have Qn as a normal discharge at depth y, and Qc is a critical discharge at the same depth y. So your Qn becomes k under root s naught and Qc becomes z under root g. So using these equations 18 and 19, our equation 9 becomes dy by dx is equal to 1 minus q upon qn the whole square divided by 1 minus q upon qc the whole square into s naught. So you can express the GVF equation in terms of Froude number, in terms of conveyance, in terms of different discharges. And if we use the Manning's formula for a wide, considering a wide rectangular channel, so for wide rectangular channel, your properties R is equal to Y. So that property we use, then your equation 20 becomes 1 minus yn by y the whole power 10 by 3 divided by 1 minus yc by y cube into s naught. So for wide rectangular channel you can directly implement this formula. So there are different versions, and finally using our equation 3 and equation 9, so the d by dx that can be expressed as s naught minus sf. So change in the energy slope, that is the we are not considering here datum, we are considering the specific energy slope, so it is s naught minus sf. So these are the various mathematical forms of GVF equation. Now let us understand the characteristics of flow profiles. So what are flow profiles and how they are characterized, that we will see. So the dynamic equation of GVF expresses the longitudinal surface slope of the flow with respect to the channel bottom. So it considers the surface slope and the channel bottom, and that way it relates each other. So we can use this equation to describe the characteristics of various flow profiles. So you may encounter that a flow is happening this way, a flow is happening this way. So there are different flow profiles possible, and we will analyze that. Now we are assuming that the channel is prismatic. So that assumption we are carrying forward. Now if we carefully look the relationship of the conveyance and the section factor equation, so they either monotonically increase or decrease with respect to the depth. Now this relation is possible for all channel sections except the channels which are having a closed top, or the channels of second kind like circular sections and all. Okay, so now we'll make use of we are recalling the equation 17, which was in terms of conveyance and section factor. So there are two terms basically, one is a numerator term and denominator term. So dy by dx can take two values, either it can be positive or it can be negative. There are some special cases which we'll discuss later. When it will be positive, there are two conditions for dy by dx to be positive. So the first condition is either both the numerator and denominator are positive or both are negative. So that will yield the positive value of dy by dx, and if either of them is negative, then your dy by dx is negative. So what is the meaning of dy by dx being positive? That is, your flow depth would increase in the direction of flow. So we are considering this x direction. So flow depth would increase in the direction of flow, that is the dy by dx is equal to positive, and dy by dx is equal is negative, that will be the flow depth which will decrease in the direction of flow. So it will be something like this. So when dy by dx is positive, it is called a backwater curve, and when dy by dx is negative, it's called a drawdown curve. When we are drawing down something, it was likely to fall. Okay. So as I mentioned, two conditions, the numerator and denominator. So based on that, we can get the variations in dy by dx. So as I also talked about the variation of dy by dx with respect to your conveyance and section factor, so we can see that uh, they are monotonically increasing and decreasing function with respect to depth. So let us consider the very first case. Uh, if your dy by d that is the numerator that is positive and the denominator is also positive. So what does it imply? Your y is greater than yn and y is greater than yc. So if y is greater than yc, your flow has to be subcritical. If we look at the this curve, specific energy curve, so this will be your yc point, and any depth greater than yc, that will be subcritical zone. So that is one comparison. So how do you frame up this? So y greater than yn and y greater than yc. So again, two conditions are possible in this. So the first condition is that y greater than yn greater than yc. So when yn is greater than yc, it will be a mild slope channel. So subcritical flow on a mild slope channel can have backwater curve, and when y is always greater, so in this case, so when y greater than yc greater than yn, so when yc greater than yn, we have steep slope channel. So subcritical flow can also on a steep slope channel will also result in a backwater curve. Okay, parallelly we'll deal with the other case also, that is drawdown curve. So here the numerator is positive and the denominator is negative. So you have a case where your y is less than yc. So when y is less than yc, it comes somewhere here, so it becomes a supercritical flow, and here it is yc greater than y and greater than yn. So making this inequality, only one case is possible. So when your yc is greater than yn, it is a steep slope channel. So when supercritical flow happens on a steep slope channel, you get a drawdown curve. So we'll in the next lecture we'll visualize and sketch all these profiles, and it will be more clear. This is the first case. Second case, when your both numerator and denominator are negative, so your y is less than yn and y is less than yc. So when y is less than yc, it is a supercritical flow. Again, two cases are possible, that is y less than yn less than yc. So this condition, yn less than yc, so that is a steep slope channel, so supercritical flow on a steep slope channel. And next condition, when less than yc less than yn, so this is a mild slope channel, yc less than yn, so again supercritical flow on a mild slope channel, so that will result in a backwater curve. Coming to the drawdown curve, we have the numerator as negative and denominator as positive. Since y is greater than yc, you will have a subcritical flow, and arranging the inequality, we have yn greater than y greater than yc. So yn greater than yc, so that is a mild slope channel. So subcritical flow on a mild slope channel will again yield a drawdown curve. Now what happens when your dy by dx is equal to 0? So when your dy by dx equal to 0, your water surface becomes parallel to the channel bottom, and your when we put that in equation 17, this LHS becomes 0, so 1 minus kn by k the whole square. That means y is equal to yn, and when your depth of flow is equal to normal depth, it is a uniform flow. So this is a special case where we treat it as a uniform flow. So there can be three types of uniform flow. Uniform critical flow, where y equal to yn equal to yc. Uniform subcritical flow, where y is equal to yn but yn is greater than yc. And uniform supercritical flow, that this yc is greater than yn is equal to y. Okay, so that is about the characteristics of flow profiles. One small part with that will conclude that what will happen when your y tends to yn. So when your y tends to yn, your dy by dx will tend to 0, and your water surface approaches the normal depth line asymptotically. So that is one case. And when y tends to yc, your dy by dx would tend to infinity, and the water surface would meet the critical depth line vertically. So when we are sketching the flow profiles, this will be very clear. Uh, so when the hydraulic jump forms when the flow changes from supercritical to subcritical flow. Okay, so uh, let us say this is because when it will touch the critical line, when it has to cross that critical state, so it has to touch the critical line. So but crossing the critical state, that is from supercritical to subcritical, we need essentially a hydraulic jump, and where high energy loss takes place. So in that case where a jump formation is there, our equation 17 is no longer valid, because hydraulic jump is a rapidly varying flow. So at that condition, the hydrostatic pressure distribution is no longer valid, and which is violated, which is our basic assumption to derive the GVF equation, and that is because of the very sharp streamlines. Okay, so that is there. Then we have the last case where your y tends to infinity if your dy by dx is equal, it tends to s naught. So in that case your y tends to infinity, so that means the water surface meets a very large depth as a horizontal asymptote. So these are all conditions where we can characterize the flow surface profiles, and in the next lecture we will understand how to analyze the gradually varied profiles. So till then, have a nice day, and we'll meet next time.